Now let's ask a question to ourselves. How much of a drug do I need to give in order to rapidly reach this target plasma concentration, denoted by the CP, at a steady state? Well, to answer this question, we need to use a loading dose, which is going to be defined as the loading dose equals this plasma concentration, this target plasma concentration that we're hoping to achieve, times our volume of distribution of a drug, all of that divided by capital F. And capital F, remember, we saw it earlier, is bioavailability. So let's quickly look at the name here, the loading dose. The loading dose gives us a clue on what its function is. The goal for the loading dose is to rapidly give a bolus of drug in hopes of reaching this plasma concentration as quickly as possible. We're trying to achieve this target plasma concentration. How big of a dose do we need to give? So what factors are we dealing with the loading dose? The plasma concentration, right here, the C sub P, is the target concentration of a particular drug in the plasma. Now, if we want a large amount of certain drug to be in the body, we would give a larger dose. That makes sense. So since the plasma concentration is in the numerator, a larger target that we're hoping to get for means we're going to need to give more drug, so a larger loading dose. Same with volume of distribution. A higher volume of distribution means you need more drug to cover this large distribution, so a larger loading dose is going to be needed. Then lastly, we divide by bioavailability here because not all drugs are fully utilized in the body at 100%. We got to think back just a few slides. IV drugs skip the first pass effect, so IV bioavailability is always 1. The loading dose divided by 1 is still the loading dose. However, what happens if only 50% of the drug that is given actually becomes utilized before it gets metabolized? So I'm saying, what happens if we give an oral medication and only 50% of it actually makes it to its target before getting broken down? Because the other 50% gets hit by the liver. Remember, it's the first pass effect. And remember earlier I said oral medications, it's somewhere less than 100%. Well, if I'm telling you that the bioavailability is only 50% of a given drug, it means only 50% of the drug is reaching its target. So we need to divide by 0.5. Anything divided by 0.5, you double what you need to give. So you're going to need to double that loading dose that you need to give because only 50% of the stuff that we give actually makes it to its target. That's the effect of the first pass effect. Now what about the question, we just gave a patient a loading dose of a drug. How much of that drug do I need to keep giving in order to keep that patient at a target plasma concentration? Well, our answer is going to be given via the maintenance dose. The maintenance dose is equal to our target plasma concentration times the clearance times a dosage interval, which is going to be denoted by tau, all of that divided by capital F, which was our bioavailability. Note that the maintenance dose equation is going to be dependent on the clearance. Remember from our last slide we had our loading dose. Our loading dose was equal to our target drug plasma concentration times a volume of distribution, all of that divided by our bioavailability. So in patients with renal or liver disease, which is associated with an impaired clearance, the loading dose is not going to change because it doesn't have clearance in the equation. However, our maintenance dose will have to be adjusted. It'll have to be smaller. Well, why is this? Because when you have liver or renal disease, you cannot clear the drug as fast, so the drug will stay in the body. If you have more drug staying in the body, smaller doses are required to maintain the target plasma concentration of a drug. Now we also have this new factor to consider in our maintenance dose equation, the dosage interval, or tau. Assuming that we are not continuously giving the drug, how often are we going to need to keep giving our drug? Well, the dosage interval is the time between doses. It's found in the numerator of the equation, and if the dosage interval is big, it means there's going to be a long time between doses, so we'll actually need to give a larger maintenance dose to maintain this target plasma concentration. What do you think will happen to our maintenance dose if we changed the dosing interval from every 8 hours now to every 2 hours? So if we dose our medication every 2 hours instead of 8 hours, we'll need to give a smaller maintenance dose to adjust. Because we're giving the drug more frequently, we'll have to give smaller doses of the drug. Just remember, the dosage interval is in the numerator, so maintenance dose and dosage interval are directly related. Even though we're dealing with dosage intervals, just remember that the steady state of a drug will actually depend on the drug's half-life instead of the dosage intervals. Let's walk through together a really tough practice question now to reinforce what we just learned about the pharmacokinetics and the different aspects of pharmacokinetics. So we have a new antihypertensive drug that is being tested in clinical trials. A 20 milligram IV bolus of the drug is administered to a volunteer, and the graph shown here illustrates the decline in plasma concentration over time. So my first question is, what is the half-life of this drug? So we can figure it out by actually taking a look at the graph here. The half-life is approximately 10 hours, and we can find that out from the graph. So I want to point out two things. First, we have a y-axis, which is a log scale. So if you need to go read up on what a log scale looks like, now would be a good time to do so. It's not in nice little increments. And then also on our x-axis, we do have nice 10-hour intervals here. So first, let's look at our time zero. Since this is a log scale, we know that the concentration at time zero is approximately 80 nanograms per milliliter. Now what we would want to do is we would find about where is 40 nanograms per milliliter. And since remember this is a log scale, 40 would be approximately right there. So let's trace it over and down. Oh look, it's about 10 hours. I'm going to clear that off. Our half-life in this situation is approximately 10 hours. Alright, so let's dig a little bit deeper. What is the volume of distribution now? Well, for figuring out the volume of distribution, we need to remember what the formula is. So the formula for volume of distribution is the amount of drug in the body divided by plasma drug concentration. So, how do we figure out how much drug is in the body? Well, up in the question stem, we find out that we put 20 milligrams IV bolus of the drug to the body, to the volunteer. So we have a 20 milligram bolus. Now we need to figure out how much is in the plasma. So we look at time zero here. I already said that it was about 80 nanograms per milliliter. So that's what we'll go with. 80 nanograms per milliliter. I'm going to spare you the time on the calculation here. It's approximately equals 250 liters. So notice that I put it in liters because like I said, volume of distribution is usually expressed in liters there. So what if I told you, what if the drug was given orally instead of intravenously and it had a bioavailability of 0.5? Because remember in IV bolus, you're not going to have any first pass effects, so we can assume that the bioavailability will be 1. However, what if our drug is now given orally and I tell you that the bioavailability is 0.5? Well, that means, since it's 0.5, it means that only 50% of the drug is surviving the first pass effect and actually making it into the bloodstream, ready to go. So, I'm going to tell you that what we do is we multiply the body by the bioavailability, and I told you that the bioavailability is 0.5, so 20 times 0.5 is actually 10 milligrams. So our new volume of distribution, if this drug was given orally with a bioavailability of 0.5, it would be 125 liters. So that's just a side scenario that you may encounter. I'm going to cross this out so we don't get confused later on, because we have a little bit more work to do. So now we just figured out the volume of distribution. Let's figure out what is the clearance of this drug given that the rate constant of elimination is 0.07 hours to the negative 1. So what we'll need to do is we'll need to figure out what is the clearance formula. So we'll have to manipulate it just a little bit. Clearance is equal to the rate constant of elimination times the volume of distribution. So we have those values. We just figured out the volume of distribution and I already gave you the rate constant. So let's figure this out. So it would be 0.07 hours to the negative 1 times 250 liters. That would give us a clearance of 17.5 liters per hour, or put another way, it would be 292 milliliters, 92 there, per minute. So just using some different calculations there, you could either express it in liters per hour or milliliters per minute. So now let's say that we infuse the drug at a rate of 0.05 milligrams per minute. What will the steady state concentration be? Do we have all the tools to answer this? Well, we do. We need to remember that for constant IV infusion of a drug, the maintenance dose is equal to the plasma concentration target that we're trying to achieve times our clearance. Well, we're not really going to have to figure out our timing interval because we're giving a constant infusion, and we don't have to do bioavailability because I already told you that it's an IV bolus. So what's left is we have our maintenance dose and we have our target plasma concentration and then also our clearance. We want to know the plasma concentration at steady state, which is equal to maintenance dose. So here we go. We want to find this value out. So what we'll do is we'll just divide maintenance dose by clearance. So it'll be target plasma concentration is equal to maintenance dose divided by clearance. So we're given that our maintenance dose, our rate, is 0.05 milligrams per minute. So I'm just going to input this in, 0.05 milligrams per minute. Our clearance, handily, we calculated that. And since I did give us the milliliters per minute, I'm going to use that because we have milligrams per minute. We don't want to get confused with our units, so divided by 292. That will give us a steady state concentration of 0.17 micrograms per milliliter. So that would be our steady state concentration. So we just did a ton of work to figure out what our steady state concentration is given all of this value. We just have to manipulate what we are given. So now my next question is, what would happen to the plasma concentration right here at steady state if we doubled the infusion rate? So our infusion rate, our maintenance dose was 0.05. What if I now told you it was 0.1 milligrams per minute? Well, simply our steady state concentration would double as well. So 0.17 micrograms per milliliter would now be 0.34 micrograms per milliliter. Our target concentration plasma value would also double to that. How long would it take to reach the steady state plasma concentration for each infusion? Before we start writing out equations and making calculations, let's take a quick step back and think about this question. Both infusion rates are constant, even though one is twice as fast as the other. A drug infused at a constant rate takes usually 4 to 5 half-lives to reach its steady state. It doesn't matter how fast we're infusing, this is an important point to remember. It is going to be the same. So we're about halfway done with the pharmacokinetic and pharmacodynamic section of pharmacology. We dove into the deep end right away with some really important concepts. The material here that we are discussing does not have as much memorization of facts, but rather the conceptual concepts that will be important for test day. Notice how we haven't covered many specific drugs so far, despite being in the pharmacology section. This is because many system-specific drugs are located in that section of the first aid book and video series. For example, many heart drugs are located in the cardiology section of the series. Most questions on test day may incorporate a bit of pharmacology and a bit of systems material, so understanding the concepts that I am talking about today is going to be very important.